Hey everybody, Dr. White here with a discussion of the normal distribution. I want to start with a problem that seems to have nothing to do at first with probability, but you'll see the point of it very soon. It's a problem that you could do in calculus too. Imagine the shaded area that you see here underneath the curve y equals e to the negative x squared, which is that thing that's symmetric around 0. And above the horizontal line y equals 0. And suppose you took that shaded area and you revolved it around the y-axis, then you would get this solid that might be thought of as an infinite sombrero, extending out in all directions. What's the volume of it? Well, we could use the method of cylindrical shells on this. We could take an arbitrary positive real number x and make a tiny thin rectangle, from like x to x plus dx, up from the x-axis to the curve. So its height would be e to the negative x squared, and its thickness is just the dx. And if we let it follow the revolution around the y-axis, then it would revolve into a little cylindrical shell. And if we were to take that shell and maybe take a piece of scissors and snip vertically somewhere along it and roll it out flat and just look at it head on, then we'd be looking at a rectangle like this. And because the circumference of the circle, 2 pi times its radius, is 2 pi x, and the height of the shell is e to the negative x squared all the way around, then the face is that rectangle with those dimensions. You don't see the dx thickness because you're looking at it head on, but it's there. And so the volume of the whole shell, which we'll call dv, is the area of its face times the thickness. And what we have to do is add up all of those little volumes. So here's the dv, and we're adding them up. X goes from 0 to infinity to catch all possible shells. That's an improper integral. So we'll set it up in the correct way. And then we need to maybe find the antiderivative of this function of x. So I've set myself that little problem, and then I'll come back and deal with the actual definite integrals. So that looks ripe for the method of substitution, because I see two pieces. I see a minus x squared and I see an x, and the one is like a constant, is within a constant multiple of the derivative of the other. So I let u be the other, negative x squared. Du is negative 2x dx, and I'm going to solve that for dx. And then I'm going to go and plug in everything that I can. So I can't do anything about the 2 pi x, but the e to the negative x squared becomes e to the u. And here is the dx. And so the 2's cancel out, so do the x's. And there's a minus pi that I'll factor outside, and I'm just left with the antiderivative of e to the u, which is, e to the u plus c. Minus pi e to the u plus any arbitrary constant would be an antiderivative for this function. So I just pick any antiderivative I like, getting ready to apply the fundamental theorem of calculus. I'll pick the simple one where the arbitrary constant is 0, and I need to evaluate it between the 0 and the n, and then take the limit as n goes to infinity. So plug in my n, plug in my 0, and subtract. And I think about things, and e to the minus n squared goes down to 0 really fast as n goes to infinity. So the only thing I'm going to leave left was minus pi e to the 0, which is a pi. So kind of interesting. Some kind of relationship between e and pi, and I guess the pi creeps in because you've revolved, kind of made circles out of things. So next thing I'd like you to do is just think about that sombrero solid whose volume we've just found. I claim it's exactly the same solid as this. If you took a function of two variables, a z here is a function of x and y, and z is e to the minus x squared plus y squared. And so, that being a function of xy, its domain is like the entire xy plane, and then you can imagine a z-axis, sticking straight up out of the xy plane, and you could try to graph the function over that, and that's where you would get the top of this sombrero-looking thing. And the xy plane itself would have the equation z is 0. And I'm saying that that sombrero is that we just looked at and found the volume by cylindrical shells, the thing that we rotated around the y-axis, is actually the same as the volume underneath this function of two variables and over the xy plane. And one way to convince you of that might be to Google the graph of this function. And so let's just ask almighty Google for the graph of e to the minus x to the 2 plus y to the 2. So I'm going to head to a web browser and graph of e to the minus paren. Oh, and I've already done it before, so I'll just go ahead and use my browser completion. And wow, it popped up a graph, which is pretty amazing. Now it just set the x to be from minus 10 to 10 and the y to be the minus 10 to 10. I'm going to make that maybe more like a minus 2 to a 2, and I'll let the y vary from minus 2 to a 2. And I'll let them keep the z's like they want, and so yeah, it looks like we're getting that sombrero shape that we imagined. Yeah, pretty cool. Alrighty, and if you want to be a bit more mathematical about it, you think about here's the xy plane, and you imagine the z-axis coming straight out of the page towards you. And if you've got a point in the domain, it would have coordinates x, y, and its distance to the origin would be the square root of x squared plus y squared, right? And so if you're thinking about what is the z at that point, it's equal to e to the minus square of the distance of the point xy from the origin, okay? And that's exactly what's happening over here. When you rotate around, you're keeping your same distance from the origin and creating the curve. So, and here you got e to the minus x squared, so that's e to the minus distance to the origin. So I think I hope I've convinced you that these two solids are the same. So I'm going to just find the volume of the solid conceived of in that second way as the volume underneath the e to the minus x squared plus y squared function. And so here I'm going to have to kind of wave my hands a bit for those who haven't had multiple integrals yet, which you'll meet in Calc 3. So you have to integrate over the entire xy plane. So we imagine that y is allowed to vary from minus infinity to infinity, and x is allowed to vary from minus infinity to infinity, and that captures the entire xy plane. And what you want to do is get the volume underneath that curve over the plane. So we've got to find what we call a double integral here. And we know that it's pi because we've already found this volume, but I'm going to just find the volume another way, okay? So I take this volume and I think, you know what? This thing here, I can think of as a regular old definite integral where I've got a function of y. See the little dy here? Got a function of y. And so as far as, y is concerned, the x that's sitting there is just a constant. And I've got to find, the area underneath that curve. And it's going to depend on x, of course. But, the x is a constant as the y goes from minus infinity to infinity. So I think about that one a little bit, and I realize, well, I could use a property of exponents to separate things out like this. And as far as y is concerned, e to the minus x squared is a constant. So we could factor outside of that integral sign. I'd be left with this. Okay. Now, that's a definite integral. It comes to a fixed number. So it's a constant as far as the x in this integral is concerned. So it can factor out. Okay. And when it factors out, you're left with just this for that outside integral. Now, this here, when I look at it, it differs from this here and only in having a different dummy variable. They really represent the same area. They're both the area under the y equals e to the negative x squared curve and above the x-axis. So I'm just going to go ahead and change the dummy variable from a y to an x here. And so now I've got the exact same quantity multiplied by itself, so it's the thing squared. And so what I've learned is that the square of that is pi. So this is the square root of pi, which is pretty amazing. There's no closed form formula for the antiderivative of e to the negative x squared. You can try all the integration techniques you like, partial fractions, integration by parts, clever substitutions. You'll never come to a formula for the antiderivative of e to the negative x squared, but you can find that particular area using this trick of evaluating the sombrero volume in two different ways. Okay, now let's let mu be any fixed real number, and let's let sigma be any positive fixed real number. And let's wonder, like, what's the area underneath this function of x over the x-axis? And it's a very similar kind of problem. It's an e to a minus, stuff squared area. It's just, there's some constants hanging around. But if you did a substitution, if you let, for example, y be equal to x minus mu over sigma, and just like did that substitution and worked on it, you would come to some numbers times the integral from minus infinity to infinity e to the minus y squared dy, which is equal to a square root of pi. So you could continue working. And it turns out when you do that and you simplify everything, you just get a 1. And so you can look in the textbook if you want, more details, and the textbook's approach for also just finding these kind of integrals, which involves more explicitly Ch03 kind of techniques. So what we've got here, this function, it is certainly a positive number for all values of x, because e to the stuff is never 0 or negative. And also its integral is 1 over all x. And so it is the probability density function for some random variable. We're going to call that random variable a normal random variable, and we have to specify the two numbers that helped us to make it. This mu number and the sigma number. We're going to specify actually the square of that sigma number for reasons that you'll see in a minute. So it's helpful to kind of carry in mind a picture of the graph of these kind of functions. That sombrero look is kind of a bell-shaped look. And the biggest that this is ever going to get is when you're raising e to the smallest negative power you can. And if you put in x as mu, you get a 0. And that's the best you can do. Everything else is a negative number. And so the highest value occurs when x is equal to mu, as you see here. And another thing that you can demonstrate using just calculus is that the inflection points are at mu minus sigma and mu plus sigma. And so that's actually like an exercise in the textbook to take the second derivative, set to 0, and just find out that the values of x that make the second derivative 0 are indeed mu plus and minus sigma. And of course, this bell-shaped thing is totally symmetric around that mu value. Okay, so again, we're just introducing this whole new family of probability distributions, one for every choice of a mu and a sigma squared. So we should find out about these distributions. So why don't we go ahead and get their moment generating function. So we're looking for the expected value of e to the t capital X. And so we're integrating over the support possible value of e to the dx times the chance of getting that possible value, which is that 1 over sigma root 2 pi stuff, e to this complex negative fraction stuff. And so we stare at that, and it's like you don't know what to do, so why not just kind of punt? We can at least square out the x minus mu squared. Kind of like stalling for time and hoping something good will happen. And we've got 2 different powers of e, so let's just use a property of exponentials to make them 1 power of e. Now, when you do that, you can actually put everything like this over this 2 sigma squared. And the reason is that if you look at this, that you've got this minus 2 mu and then the x that you had here, but you've also got a minus sigma squared t x, okay, times a 2, which is the same stuff that you had here. So we've just stuck that like where it belongs over here so that you can factor out like an x. Okay, and then staring at this is not a perfect square anymore because I've thrown some things into the middle term, but I could complete the square on this part. And so, when you got to complete like a square in an x squared plus a kx type of thing, you just add on the k over 2 squared. So this time the k is this minus 2 mu squared plus sigma squared over t. And so k over 2 of it would be a minus mu squared plus sigma squared t. And so you add on mu plus sigma squared t squared. And that would make this a perfect square. But of course, you're going to have to subtract that stuff off in order to not change the quantity that you're actually working with. Okay, and then somewhat perversely, we're going to separate out again. This is a perfect square, and it's equal to just this difference squared. And so we've got this stuff, which we'll pull out as its own little power of e. And then we've got this stuff left, which does not have any x's in it, you'll notice. It's actually a constant. And if you play with it a little bit, you'll see there's some cancellation. And it's a constant as far as the x is concerned in this integral, so you can just factor it outside of this integral, and here it is. And then you just stare at what's left inside the integral. And you realize, wait a minute, that looks like the formula for the PDF of a normal mu sigma squared, except it's not. It's a normal where instead of a mu, there's a mu plus sigma t squared. But everywhere else, the sigma shows up where it was supposed to in the PDF. It showed up here like a sigma, and it showed up here like a sigma squared. So actually, what you are doing here with this integral is you are integrating the PDF for a normal mu plus sigma squared t, comma sigma squared random variable. And you're integrating it over its support. So you have to get 1. And so you're left with this. This kind of technique is just going to it's something you'll keep taking advantage of over and over again. You get a tough integral, but if you can relate that tough integral to some kind of probability property, like that the integral of a PDF has to be 1, or maybe you can find that the integral is the integral that gives you the expected value for some random variable that you know about. Then you don't have to evaluate the integral. You can just use, facts about the random variable. So there's a little bit more simplification that can be done, and you end up with this. So this is what you want to memorize like crazy. E to the mu t plus sigma squared t squared over 2 is the moment generating function. And then if you hit the textbook, you'll see how they take the first and second derivatives and evaluate them as 0. And you find the expected value of x is mu, which just seems totally right because the PDF is centered at mu. And the variance turns out to be sigma squared, and that's why we use sigma squared as the second number when we talk about the normal distributions rather than just a sigma. It's just like reminding us, hey, that's variance. So the sigma number is actually the standard deviation of your normal random variable. Now, there's a special normal random variable. The one whose mean is 0 and whose variance is 1 is called the standard normal distribution. We often say capital Z for short. And I want to show you something interesting. If you take any normal distribution and you transform it, so you little function of that random variable, x minus its mean divided by its standard deviation, call it W for now. That new random variable says how many standard deviations x is going to turn out to be above or below its expected value. And I'd like to find the distribution for capital W, the distribution of this, what we call standardized version of x. So I want to know the chance that capital W is less than or equal to little w. And capital W is this. So I just solve the event for x. And I know the PDF for capital X. So to find the chance that capital X is less than or equal to this number, I'll just add up the chances from minus infinity to that number, chance to be about x, f of x dx. So I stare at it, and it's a tough integral, so I decided to do a little substitution, regular old use substitution, but I'm going to use, I'll just go ahead and use a little z for my substitution. Let's let let's let z be x minus mu over sigma. So dz, when you do the derivatives, would be 1 over sigma dx. And so dx would be sigma dz. And so I do my replacements. I think I got like a wrong, I wonder if the top is wrong here. Let me see what's inside. So this stuff here doesn't have, it just stays along what it is. But this stuff is actually a minus z squared. Okay, and the dx, I'm writing it as sigma dz. I'm wondering about the top here. Do I have that right? So here is an x equal to mu plus sigma w. Okay, so let's put in a mu plus sigma w there for x and see what the z ought to be. Mu plus sigma w minus a mu, that would be sigma w. Divide by sigma, that would be w. Oh, so I had it right. That top now needs to be a w. Okay. And I look at this a little bit, and if I write the minus z squared as minus z minus 0 squared over 1 squared, which I can totally do, and the sigmas, they cancel out. But I'm just going to stick a 1 next to the square root of 2 pi. Then when I stare at that, I realize that is exactly asking for the probability that a standard normal is less than or equal to w. So the chance that capital W is less than a number is the same as a standard normal is less than that number. The capital W and the standard normal have to have the same probability distribution. They have the same distribution. So this is distributed like a standard normal, mean 0, variance 1. So when you standardize a normal, you get to another normal random variable whose mean is 0 and whose standard deviation is 1. That's nice. And that's actually, so that's actually done in the book. Now there's something else that the book does that I'll just go ahead and ask you to read. If you take a normal random variable, and if you standardize it and square it, then that resulting function of the random variable, square of a standard normal, actually has a chi-squared distribution with 1 degree of freedom. It's just hacking around with integrals, kind of like how we've been doing. Look at it in the book. It's neat. And this may give you a little insight into why we say that the parameter number, the R number, for chi-square random variables is called a degree of freedom. Because, like, imagine that you give yourself the task of throwing a dart at the real number line. Okay, and so the dart's going to land somewhere on the real number line. It's like you're incredibly accurate about your y direction. No variance there. You're going to have your y be 0. But you're not quite accurate on the x direction. You're aiming at 0, but you can make some error either way. And let's say that the chances for the error to be different sizes are given by a normal random variable, mean 0, standard deviation 1. So on average, you're getting it right, but typically you could easily be a unit or so away from the origin when you throw that dart. Then the square of the amount that you are off is a chi-square with 1 degree of freedom. So the degree of freedom, the 1 degree of freedom, is like that one dimension that the dart can wobble around. See? So that's probably not too convincing, but I'll give you more convincing on that when we have the math power to do so, as to why the parameter is called degrees of freedom. Here's an interesting little side fact. Say that x is normal mu sigma squared. What would be the distribution of like a constant times x, like say a times x? You might expect that it would be normal, because when we took x minus mu over sigma, we got another normal, and maybe just a constant times a normal is a normal. But let's see, could we actually prove that, and could we find out what normal it would be? Well, how about we look for the moment generating function of this new random variable? So I'll call it w, okay? So I want the moment generating function of w, and of course that's got to be a function of any real number t. So I do the expected value of e to the t capital W. So that's the expected value of e to the t a times capital X. And I could just put parentheses around the at. And I realized, oh, that's the definition of the moment generating function of x at the value at. Now, x is a normal random variable. And so, like you got to memorize, the moment generating function for a normal is e to the mu t sigma squared t squared over 2. Okay. So if I put in an at for a t, then I get an e to the mu at sigma squared a squared t squared over 2. See, the at squared is a squared t squared. Now I can put the sigma squared a squared together as an a sigma squared. And I can put the mu a as a mu. And then I look at this, I stare at it, and I realize, hey, that's exactly the moment generating function for a normal random variable, where instead of a mu, you've got an a mu. And instead of a sigma squared, you've got an a sigma squared. So what we've just learned is that a constant a times a normal random variable is also normal, and the mean is a times what it was before, and the variance is, I guess it's going to be a squared times what it was before. Kind of neat. One more example, exercise 9 in the book. Say that W is the square of a random variable that's normal with mean 0, variance sigma squared. Could we find the distribution of W? We could probably work using whatever, integral work was done in the book for that theorem back here. But we could also maybe just try to use that theorem. Let me see. So I'm thinking about my x variable here. And I'm going to do 1 over sigma times x. So constant times x. We've just figured out that that's another normal with constant times mean, constant times standard deviation squared as the variance. And so I'm getting normal 0, 1 out of that. So this is normal 0, 1. Therefore, its square has to be chi-square 1 according to the theorem in the book. So if x squared over sigma squared is chi-square 1, then I wonder what W would be. See, here's W. So we got W over sigma squared is chi-square 1. We're actually like not finished with this problem. Because we need to know like what would be the distribution of sigma squared times a chi-square 1 random variable. So that's still something to something to kind of think about, and I'll let us think about that, and we'll probably figure it out. Huh? All right, enough said, I guess, about section 3.3. I will see you soon.